PreAP, PreCalculus, Notes 4.3. In our previous section, we learned the rational root theorem. In this section, we're going to use the rational root theorem to help us find irrational real zeros as well as imaginary roots. Real roots, emphasis on real, can be one of two types. They can be rational and they can be irrational. Rational roots, the rational root theorem helps us find directly. Irrational roots could be helped to be found using the rational root theorem indirectly. Consider h of x. This is 3x to the fourth minus 8x cubed minus 12x plus 24x plus 9. It's pictured below. Let's just talk about a few things. Well, let's answer this question by talking about these things. What three things about the graph make sense after investigating the equation? Well, the equation has a constant of 9. The graph has a y-intercept of 9. That makes sense. The equation of h of x has a constant equal to 9, and the graph of h of x has a y-intercept of 9. That makes perfect sense. Something else that makes sense? The degree of this polynomial is 4, and this has 4 roots. The degree of h of x is 4, and the graph of h of x has 4 roots. So we're 2 for 2 for things making sense. Third thing that makes sense, since the leading term is even degree and the leading coefficient is positive, this graph is going to rise on the left and the right. So I want to say that h of x is even degree with positive lead coefficient. And the graph of h of x rises on both sides meaning as you go left or right. That's old stuff that we've learned, and we're just reviewing it and putting that together. What conclusion can you draw about the 4 roots of the function? Explain your reasoning. Well, looking at the graph, we can say that 2 of the roots are negative and 2 of the roots are positive. And we can say that each of these roots has a multiplicity of 1. And it's odd multiplicity of 1 because h of x crosses the x-axis without changing concavity. At each root. What's the goal of this lesson, you might be asking yourself? Well, as previously stated, the goal of this lesson is to use the rational root theorem, that was in the previous section, to aid us in finding all of the roots of the function, whether they be rational, irrational, or imaginary, because that's our ultimate goal. Let's find all these roots, yo. Make a list of the rational roots that the rational root theorem guarantees are possible. And we are referring to this function right here. So I want to make sure that's clear. So to make that possible rational roots, this is a review of last section, we're going to take the factors of 9 and put that in the exponent, positive and negative factors. We're going to take the factors of 3, the lead coefficient, put that in the denominator. Every combination of number on the top and the bottom would be a possible rational root. I'm not going to actually write them all out. I just don't think that that's very helpful. From this list, which roots appeared to be the roots of the graph of h of x? Perform synthetic division to verify this. Now, this is what we did in the last section. This is just a review. Everything we've done so far has been from previous sections. This particular part, right from the last section. So, highly possible rational roots. Can we make sense of this one? It's something that's between -1 and -2. And we don't have that as a choice. None of these rational roots are between -1 and -2. So we can't even estimate what that would be based upon this. How about between 0 and -1? We could do a -1/3, and that's our only choice. So maybe -1/3, that's highly possible. And then here between 1 and 2, once again, none of these choices, none of these combinations of top numbers and bottom numbers would give us a number between 1 and 2. So that's not going to work. 3 is highly possible, and that's found by taking 3 divided by 1 or 9 divided by 3. So from this list, which appear to be highly possible rational roots, that's perform synthetic division. Let's do that. So let's take the coefficients of this polynomial, p of x, and let's go easy and let's divide it by 3. 3 and 0 is 3. 3 times 3 is 9. 9 plus -8 is 1. 3 times 1 is 3. Add, you get -9. Multiply, you get -27. Add, you get -3. Multiply, you get -9. Remainder 0. We expected that. Now let's divide by -1/3. Hopefully this doesn't get too crazy. Add, multiply, and -1/3 of 3 is -1. Add, multiply. -1/3 of -9, two negatives you divide, you get a positive. 9 divided by 3 is 3, so that works as well. So these two that we thought were going to work actually did. So what are we left with? We don't have any guesses on what this is going to be. So one of our factors, if 3 is a root, is x minus 3. Another factor, if -1/3 is a root, is x plus 1/3. And then our final factor is this fella. This is a constant. This is 0 times x. This is 3 times x squared. So that's 3x squared minus 9. Let's see if we followed the directions here. Divide h of x by one of the associated factors, did it. Then divide by the other associated factor, we did it. This is what we're left with, okay? One factor, two factors that we got that were highly possible from the rational root theorem, and then we got this one. You have just divided the degree 4 function twice, so your resulting polynomial is a quadratic. Resulting polynomial is referring to this fellow right here, also known as a depressed polynomial. This function's roots will be the remaining two roots, which will be irrational of h of x. find these irrational roots. So if we take this last factor and set it equal to 0, maybe we're lucky enough we can just solve this equation. We are lucky enough. We can solve this equation. When you initiate a square root on both sides of the equation, you're always going to do plus or minus. So without doing anything too crazy, we got that the other roots were plus and minus the square root of 3. So all the roots for p of x in ascending order, negative square root of 3, negative 1/3, positive square root of 3, and 3. Just to sum up, we got these fellas from the rational root theorem. We got many possible rational roots. We narrowed it down to these two based upon how it looked in the graph, and we could have been wrong about those. Turns out we weren't wrong by using the synthetic division. We got these two roots, plus and minus the square root of 3, by taking our depressed polynomial, setting it equal to 0, and solving it. Let's do another. Consider the function f of x equals 2x to the fourth minus x cubed plus 7x squared and minus 4x minus 4, whose graph is pictured below. What do you notice about this graph that does not make sense based upon the degree of the function? The previous question was what makes sense? What doesn't make sense about this? Well, this is a fourth degree polynomial. And the fundamental theorem of algebra guarantees 4 roots because of that. So let's write that down. F of x is degree 4. And the fundamental theorem of algebra guarantees 4 roots of f of x, but the graph only shows 2 zeros, each with a multiplicity of 1. And it doesn't take a rocket scientist to see that 2 zeros, each with the multiplicity of 1, that only counts for 2 of the roots. We're supposed to have 4. That's what doesn't make sense. What conclusion can you draw about the 4 roots of the function? Explain your reasoning. Well, based upon what the graph shows, we know that f of x has 2 real roots. One being positive, one negative. Let me bring this graph down here just so we can gander at it while we're talking about it. So we know one's positive, one's negative because it clearly shows. This is the negative one, this is the positive one. Each with a multiplicity of 1. How do we know the multiplicity is 1? Because f of x crosses the x-axis without changing concavity. So that means there must be 2 other roots. And since they're clearly not any place here, they've got to be imaginary. F of x has 2 imaginary roots. Make a list of the irrational roots that the rational root theorem guarantees are possible. So let me get rid of this fella, and let me just copy this down so we can gander at this while we're discussing this. All right, so the possible rational roots. Factors of -4, plus or minus 1, plus or minus 2, plus or minus 4. Factors of 2, plus or minus 1, plus or minus 2. So any combination of those. And then from this list, which roots appear to be highly possible? I'm just going to copy this up here so I can see it. You don't need to write it twice. So 1 looks like a dead ringer. This fellow over here, I mean, -1/2 would be great if it was a choice, and it is, 1 divided by 2. So that's what I'm guessing. Pretty confident, but I'm not 100% sure. So I need to test this to see if this actually is true. To test it, I'm going to divide synthetically the coefficients of the polynomial f by the root that I think it is, which is 1. 2 plus 0 is 2. 1 times 2 is 2. -1 plus 2 is 1. 1 times 1 is 1. 7 plus 1 is 8. 8 times 1 is 8. -4 plus 8 is 4. 1 times 4 is 4. So that worked out. Lovely, as they say. So then let me synthetically divide by -1/2 to see if things go just as smashing. 2 plus 0 is 2. -1/2 of 2 is -1. -1 plus 1 is 0. -1/2 times 0 is 0. 8 plus 0 is 8. -1/2 of 8 is -4. Lovely. So here's what this does for us. Since both of those work, we know that f of x by the factor theorem, since 1's a factor, x minus 1 is a, since 1 is a root, x minus 1 is a factor. Since -1/2 is a root, x plus 1 is a factor. This is my depressed polynomial, which is going to be 2x squared plus 8. And that is the fully factored form of this. I shouldn't say fully factored. We could factor a 2 out of this. So it's not fully factored. You've just divided a degree 4 function twice. So your resulting polynomial is referring once again to this fella, is a quadratic. This function's roots will be the remaining 2 roots, which will be imaginary. So if I take 2x squared plus 8, set it equal to 0. If I divide, let's say I subtract 8 from both sides, and then divide both sides by 2. The square root, if I square root both sides, you do plus or minus. The square root of a -4 is 2i. So all the roots of this problem, we have -2i, positive 2i, -1/2, and 1. To sum up, these 2 rational roots came from the rational root theorem and looking at the graph, and these 2 came from taking the depressed polynomial, setting it equal to 0, and solving it. I'm going to stop this half of the notes here, and the rest of the notes is a few more examples and then summarizing what it is we've done so far. the examples we've done so far, we were able to solve the quadratic directly. In the next part of the notes, we will not be able to solve it directly.